Okay, today we're going to use trapezoids instead of rectangles. Did you lose yours? Oh, okay, you came in. How do you find the area of a trapezoid? Okay, base 1 what? Plus base 2. Divided by 2 times 1/2, same thing. There's one more piece. Times the height. This is the area of a trapezoid. Okay? We're going to do the same thing as yesterday, except we're going to use trapezoids to find our height. So basically, we're going to take a curve and we're going to make trapezoids. See how these are trapezoids? Okay, parallel sides, non-parallel, like these are parallel bases, right? And then these would be the non-parallel sides, okay? So they're going to be trapezoids where the, like this height is always going to be perpendicular here. Trapezoids. All right? So, this is our process. Determine the number of trapezoids. Remember, that's something that I'm going to give you. Once again, that's going to be n. Okay, instead of the number of rectangles, it's now the number of trapezoids. Okay? Yesterday, we determined the width of each of our rectangles. Since our trapezoids look like this under our curve, okay, what was the width yesterday is now going to be considered the height of our trapezoid, okay? So we're going to determine the height of each trapezoid, and that is that b minus a over n. Okay? It's going to feel like the width, but it's really the height. It's the distance between the two bases, okay? Okay. This trapezoid is sitting under the curve. Those are the points that are hitting the curve, okay? So our bases are determined by the function value. Okay, the function height is going to determine how long the bases are of our trapezoid. Then we're going to find the area of each trapezoid, and what do?
Sum it all up.
We add them up. Okay, so we're going to go to your foldable, and we're going to do that fourth example. When we're done, I'll give you scissors to cut those, but for now, just go with the flow, okay? Okay, so on the picture of your foldable, let's go ahead and draw in our trapezoids. Oh, I guess flip it open, and let's remind ourselves that n is 4, and to find that change in x, we take b minus a over n, which is 1/2. So what we're going to do, we're going to take the function value at 0 and the function value at 1/2, and we are going to draw a trapezoid there. Then we're going to take the function value at 1/2 and the function value at 1, and we are going to draw a trapezoid there. Function value at 1 and the function value at 3/2. We're going to draw a trapezoid. And then the function value at 3/2 and the function value at 2, and then we are going to draw a trapezoid. Okay, so how do you feel about this approximation?
I feel like it would be more accurate.
I feel like it is going to be more accurate. Okay, so here's where it gets fun. Our area, we have 4 trapezoids that we need to find the area of. Remember, the area of a trapezoid is 1/2 times the height times the sum of the 2 bases. Okay? So we have 1/2 times. We decided that the height of each of these rectangles would be what? Which is 1/2. The width is essentially the height of each of these, okay? So we have 1/2 times 1/2 times this first trapezoid. Remember, the function height is going to give us the bases. So since this first trapezoid goes from 0 to 1/2, our bases are f of 0 and f of 1/2. Right small. Our second trapezoid, 1/2 times the height times the sum of the bases. Since our second trapezoid goes from 1/2 to 1, our bases are f of 1/2 and f of 1. All right, I'm going to have to use 2 lines. I apologize. Okay. Our third trapezoid, 1/2 times the height times the sum of our bases. Since our third trapezoid goes from 1 to 3/2, our bases are f of 1 and f of 3/2. Then, are you getting frustrated, Cole? Yeah, this is kind of tedious, isn't it?
A little bit.
There's only another way.
Is there?
Just give me a moment. Give me a moment. Our fourth trapezoid, 1/2 times the height times the sum of the bases. Our first base is f of 3/2. Our second base is f of 2. Okay, Cole is right. That was really annoying, wasn't it? Writing all of that down. Now, is there any way we could make that so we don't have to write as much down and still essentially do the same thing?
1/4.
You could do 1/4, and then you know that every function value will be there twice, other than the first and last. So you go with 1/4.
Okay, so Austin has made an observation. We can factor out this 1/2 times 1/2. Do you agree? Okay. We can factor out the 1/2 times the height. I'm going to keep it as 1/2 times 1/2 for right now. Okay? And then Austin noticed that once we do that, we're adding up all of these function values in here. But what's true about our bases? Do we use some of them more than once? All of them? Okay, this trapezoid shares this base. These 2 trapezoids share a base. And these 2 trapezoids share a base. So all but the ending bases happen twice. So what we can do is we can factor out the 1/2 times the height. We can write the first base, 2 of all of our inner bases, plus the last base. And this is a much more efficient way to find the area of multiple trapezoids. So then what we can do is we can find all of those function values by plugging the x's into our function, right, just like we did yesterday. And now it's just a matter of calculating what that sum and then the product is. Cole has 11/4. Anyone want to? Same? Okay. You can write 11/4. You could write 2.75 because it's a decimal that stops. Okay. But this is our area. A closer approximation than our rectangles. However, it takes a little bit more work, but not much, right? Okay, I promise you, you will have at least one trapezoid question on your AP test, which means on your final, you're going to have to do trapezoids for sure. Okay. All right, so if you want to write down somewhere, okay, that when we use the trapezoid method, okay, our area in general, we're going to take 1/2 times the height times the sum of the bases. And what happens is we use the first base once, the middle bases twice, and the last base only once. Our height is always our change in x, okay? It's like the width that we use for our rectangles. And our bases is always the function value there, okay? So if you need like a general formula to look at, there it is. Okay, so we're going to do another example. Are you ready? How far apart are each of those bases? Huh? Whatever the height is, they're all that same distance apart. Okay? In the last example, yes, Cole, that was 1/2. Okay? So let's do this example. We're going to find the area under the curve, y equals x squared plus 1, with 6 subintervals from 1 to 2. So in your notes, write down those pieces of information so you know where all of your numbers are coming from when you go back to study this weekend for your quiz on Monday. Okay, Grant, how do we find change in x?
B minus A,
Which in this case is?
1.
Okay. B minus A.
Over, N, which is 6.
Okay. So 1/6 is our change in x. If you don't mind, I'm not going to draw the 6 trapezoids up there. Is it okay if I save my time and we just do the math? Okay. What we're approximating is this area in here with 6 trapezoids. Okay? So, delta x, remember this is like the height of each of our trapezoids. Okay? So our area is going to be 1/2 times the height times the sum of all of our bases. Okay? Now, we begin our interval at 1. So f of 1 is a base that we only use once. Where is our next base located? Say it louder. Jake. 7/6. And how did you get 7/6? Jake. How did you get 7/6? Okay, we added this change in x to the 1. All right. So then our next base is at 7/6, but remember that has to be used twice. I'm gonna have to write smaller. Hold on. Okay. Our next base is at 8/6, and that has to get used twice. Our next base is at 9/6. That gets used twice. Now I'm going to run out of room. Okay. Our next base is at 10/6. That gets used twice. Our next base is at 11/6. That gets used twice. But then once we get to 12/6, which is 2, that's our last base, so it only gets used once. Okay? Now it's a matter of plugging it into your calculator correctly. Okay? This is going to take a little bit more patience. Let's go ahead and practice this so we make sure we get the right answer. We have time to do that today. Okay, so maybe my suggestion would be, I would not do decimals, okay? But if you're worried about like missing parentheses or forgetting multiply 2 or something, you could find like each of the function values individually, okay? And write them into your formula, and then maybe find the sum. Okay. Now remember our function is x squared plus 1. You're going to want to use that fraction feature in your calculator. Okay?
You can just add them all up. Like if you know that it's going to have all of these are going to have a base of 36, so you could just square the top number and at the end of 36.
You do that. If you find something, if you hit math and enter, it's going to be correct. Okay. Yeah. Okay.
What was Austin saying about?
Well, he was just saying that, like, 7/6 squared would be 49 over 36, and then adding 1 would be 36 over 36, so you just would take 49 plus 36. Okay, 721 over 216 is what you should be getting. Okay, this is where, like, showing work is important, because if you have all of this written down, but you get the answer wrong, you're going to get some good credit out of it, because you at least set it up correctly. Okay? If you need help with your calculator, at the end of the lesson, I'll come and help you. Right? There's one more thing we need to look at, and that is when we have data that's not in a graph. Okay? These methods that we've been talking about are really more useful when we have like some raw data. Okay? If you collect data in science, you put it into like a table, right? Right? Okay. So we're going to do some examples with what I call tabular data. Here I have a table of values. I'd like you to take 30 seconds, maybe 60 seconds, and write down this table. It doesn't have to be pretty. Just in one line, write your x's, and the next line, write your f of x's. We are still finding the area under this continuous curve. But this time, it is actually going to save us some work because they're giving us the function values. Okay? We don't have to figure out what those are. Okay, so we're going to do each of the three methods with this, and it's asking us to use three rectangles. Our interval stretches from 0 to 3. So B minus A over, we want three rectangles. How wide are our rectangles? Thank you for paying attention. Our rectangles are width 1, or our trapezoids have height 1. So this is what I like to do with tabular data, so I can really visualize where my rectangles are. Okay, we have a rectangle stretching from 0 to 1. We have a rectangle stretching from 1 to 2, and we have a rectangle stretching from 2 to 3. Those are our three rectangles. Okay, so if we approximate the area with a left endpoint approximation. Okay, those three rectangles have width of 1 times each of their heights. So if we're doing a left endpoint approximation, this rectangle that stretches from 0 to 1, what is its height? Its height is 2, okay? So we're going from the left side of the rectangle, which is at f of 0. F of 0 is 2, so the height is 2. The rectangle that stretches from 1 to 2, what is its height? 6, because that's the left function value, so that's its height. The rectangle that stretches from 2 to 3, what is its height? 4, that's the left of our rectangle, and it's its height. Yes?
So if it was right, then it would be like 6, 4, and 5.
Let's go ahead and find that, Cole. If it was the right endpoint approximation, our widths are 1. This first rectangle, yes, would have a height of 6. The second rectangle would have a height of 4. And the third rectangle would have a height of 5. Because that's the right function value for each of those rectangles. You have a question? Me? Okay. Let's talk about midpoint approximation. Our midpoint approximation. The heights are, or the widths are still all 1. What would the height of the first rectangle be with our midpoint? 4. The midpoint of 0 and 1 is 1/2, so we have a height of 4. Our second rectangle, one stretches from 1 to 2, halfway between is 1/2. It has height of 7. Our third rectangle stretches from 2 to 3, in the middle is 2.5, so we have height of 1. Doesn't this make it nice? I love tabular data. And last but not least, our trapezoid approximation. So we have 1/2 times the height, which is 1, times, okay, f of 0, which is 2, plus 2 times our next base, which is 6, plus 2 times our next base, which is 4, plus our last base, which has height 5. So this approximation is 13 points. I really like making these bars so you can really like visually see where your rectangles are. I think that's helpful. You don't have to do it if you think it's weird. If you can see it without it, that's fine. But I find it to be helpful. Okay. So we have 10 minutes left of class. I want to give you some time to start this worksheet. There is a formula at the top of the worksheet. I don't like it. Cross it out. Use the one that I give you. I think it makes more sense with what we've been doing. Okay. There are 4 trapezoid problems on the front. There are 2 problems on the back. Number 5 is very straightforward. Number 6, you're going to have to think about a little bit. It's kind of more of a challenge problem, but everyone's still required to do it. Okay. Juniors, I'm going to come around and talk to you about next year. I talked to a couple of you already.
I think we should sponsor a March Madness club.
New March Madness bracket.
Are we?
We can put them all on the wall, and then every morning we can come in.
Are you gonna do that when I was kids?
Bro, they're gonna be a 12. They're gonna be a 16. Nah, they'll be higher. They don't have any good wins this year though. They have close games against the.
Oh, one of them does have good wins.
What?